Alright, so now we've done covalent nomenclature, which is the easier of the two. So now we're moving into ionic nomenclature. And we're going to start with the easiest form of ionic nomenclature. Make sure you get this and understand this before you move on. Okay? If you are not grounded in this lesson, the next couple of lessons will just add confusion instead of adding clarity. So you need to make sure you clearly understand, and really that goes for all these, like make sure you understand the lesson you're on before you move to the next one. If you have questions, email me, message me, ask in the Facebook group. Do whatever you need to do to make sure you've got these down before you move into further on. So binary ionic. So as the name kind of implies, ionic bond is all about not sharing anymore. We're giving and taking. And they occur between a metal and a non-metal, specifically here binary. And there's only one possible way they can ever combine. So we will not use prefixes. Okay? Because like when sodium and chlorine combine, there's only one way they can do it, and that's NaCl. There will never be NaCl2. It can't happen. It's not possible. So there's only one way it can happen, so no prefixes. And then we still add the whole thing where we write the name of the metal first, but then we put "ide" on the end of the non-metal on the end, just like we did with covalent. So naming these is pretty simple. And it's really, it's even easier than covalence because you don't even have to worry about the prefixes. You just have to put "ide" on the end. So name the metal, sodium, then chloride. Name the metal, magnesium, then bromine, bromide. So magnesium bromide, and then aluminum sulfide. So naming binary ionics is really simple. You just put IDE on the end. Where it gets a little bit more confusing is when we try to go back the other way. Well, why is it that sodium and chlorine are 1 to 1, but magnesium and bromine are 1 and 2, and then these are 2 and 3? Like, why are these numbers what they are? That's a little more complicated, and that's where we're going to get into ionic charges. So, like we said with the octet rule, atoms want to get to 0 or 8 valence electrons in order to be stable. So we're going to gain or lose electrons instead of sharing them, in order to get to that 0 or 8. So metals are going to lose and form positive ions. So for example, calcium is in group 2. Because it's in group 2, it has 2 valence electrons. It's going to lose them because it wants to get to 0, and that gives it a total charge of 2+. And charges are written as a superscript up here. Just where, like with other formulas, the quantities are written as subscripts, here the charges are written as superscripts. Okay. And then nonmetals gain electrons to form negative ions. So oxygen has 6, so it gains 2 to get to 8. And once again, we write that charge up there as a superscript. For binary ionics, we're looking at just metals and nonmetals. So they will follow this pattern. Okay, so going across the periodic table, it kind of rhymes. We're skipping the transition metals for now. We will get to them later. But going across the periodic table, 1 plus 2 plus 3 plus skip, 3 minus 2 minus 1 minus zip. You may be wondering, why do we skip group 14? That's carbon, silicon, and the rest of that group. And the reason being that they just don't form ionic bonds, because gaining or losing 4 electrons is just really hard to do. It's hard to gain or lose that many. And so they just don't generally tend to form ionic bonds as elements. They'll be involved when we do some other types of ions, but right now as pure binary ionic, they don't do it. And then noble gases are 0 or zip because they don't form ions, they don't react, they don't do anything. They're already at 8 valence electrons. They don't need to do it. Okay? So like I've already said, they're always going to be written as a superscript. If there's not a number written, like with sodium and bromine, it's understood to be 1. So sodium's 1 plus, bromine is 1 minus. That's understood. So the formulas for these are going to be determined by making the charges cancel each other out. And if you are in the visual or kinesthetic type style learner, I would strongly encourage you to go and get in the free resources category, you got free downloads at the top of the web page. There's one under there called Ionic Formula Activity or Ionic Nomenclature Activity, and it is a great hands-on way. You make these cards and you arrange the cards to make them cancel each other out. It's a great way to learn how to do this. I'm going to try to model that somewhat in here, but that activity is great for those of you who are more visual or kinesthetic. All right, so for example, magnesium chloride, the ions are magnesium and chlorine, or chloride. By the way, as soon as this has a charge on it, we change the ending to IDE. So this is not a chlorine ion, this is a chloride ion. Now think about it, like when you're teeth brushing, like you talk about fluoride, because you're talking about it in its ion form, you're not talking about fluorine. Okay, and so as soon as it puts a charge on it, as soon as it has a charge, we're going to go ahead and change that ending of its name to IDE. So we're going to call this chloride, not chlorine. All right, so if you look at it, there's 2 positive, 1 minus. I need to make these balance each other out and cancel each other out. So, just some basic logic, hopefully. You see that you need 2 of these to cancel out 1 of these, because 2 1s make a 2. So 2 and 2 would cancel each other out. Therefore, the formula is MgCl2. Okay? That's the easiest way to really think about what's really going on. Okay? All right, so let's look at some examples. Lithium phosphide. Lithium's the metal, and phosphide's the nonmetal. And so you get their charges once again from the periodic table: 1 plus 2 plus 3 plus skip, 3 minus 2 minus 1 minus zip. And so this follows the same pattern. This is group 1, so it has a 1 plus. Group 15 is 3 minus. So I've got a 3 minus and 1 plus. Once again, I need to make these balance each other out. So I need 3 of these. If I have 3 positives, that'll cancel out my 3 negatives. So my formula is Li3P. Notice, please notice, there are no plus or minuses in the formula, and there are no superscripts in the formula. Okay? The formula is neutral. There will never be a plus or minus in the formula, and there will never be any superscripts in the formula. That is critical. All right, barium and oxygen. Barium's in group 2, so it's 2 plus. Oxygen's in group 16, so it's 2 minus. Once again, that 1 plus 2 plus 3 plus skip, 3 minus 2 minus 1 minus zip. Okay, if you don't have your periodic table in front of you, now's the time to do it. Okay, because you're going to need it to figure out these charges and all that kind of stuff. And so these are already equal, so we just simply write their formula, BaO. Okay. Aluminum and sulfide. Okay. This one is where some people tend to struggle because you got to think about it a little bit differently. So here's a 2 and a 3. I can't multiply this by anything to get to 3. I can't multiply this by anything to get to 2. So you got to go to the lowest common multiple, which is 6. So I need 2 of these to get to 6, and I need 3 of these to get to 6. You get Al2S3. The other way to do this is to do what people call crisscross. And with crisscross, what you do is you take this number. No, I'm saying the number, not the charge. The number comes down here, and this number goes down here. So they crisscross to go down. So the 3 goes after the Li, the 1 goes after the P, and you get Li3P. Okay? Same thing works down here. The 2 crisses down after the aluminum, the 3 comes down after the sulfur, or the sulfide. You get Al2S3. Alright? Here's where that doesn't work, and that's because these are already equal. You would get Ba2O2 because the 2's would criss down here, and then that 2 would cross down there. You just simply reduce it. Ionic formulas are always going to be reduced to their kind of like fractions. They're always reduced down to their whole number ratio. And so crisscross method works. Thinking about the balancing the charges works. So that's binary ionics. They're pretty simple. Like I said, if you're wanting some more practice, that Ionic Nomenclature activity that I have under your free resources is a great activity. You just got to cut out the cards, and it'll help you see visually. Once again, especially if you are a visual or kinesthetic learner, I cannot encourage it even more strongly than I do. That's a great activity to use to help yourself, and then it's a great activity to use for your students later to really see what's going on here and understand what's going on. Like I said, practice through the workbook, go download that activity, make sure you really understand what's going on here before you move into the next lesson, because things are going to start getting a little more complicated. All right, so I will see you in that next lesson on polyatomic ions.